Dear ladies and gentlemen, I welcome you to my presentation about fatigue design in penstocks. I'll show you the comparison of the nominal stress and structural stress method for common details in penstocks. My name is Alexander Ecker and I wrote this paper together with Harald Unterweger. We are both from the Technical University of Graz in Austria. Now I'll show you the scheme of a pumped storage power plant. The penstock is highlighted in red. These penstocks have a very long working life, and fatigue phenomena have to be considered, especially in pumped storage power plants, because the change of the water flow causes a dynamic pressure. And nowadays, with the increase of renewable energy and the intensified regulation, fatigue design can be a dominating factor. Two common details in penstocks are investigated for fatigue design with the nominal and the structural stress concept. The first detail is a thickness transition in the pipe or the penstock. A thicker pipe with the thickness T2 is connected to a thinner pipe with the thickness T1. This is done by an circumferential butt weld. Usually a bevel with a gradient of 1 to 5 is used to connect these two pipes. The second detail is a ring stiffener welded onto the pipe, also with a circumferential weld. And especially in penstocks, different load conditions can occur. This table shows different load cases in penstocks. Load case A is a load case in which only an internal pressure occurs and no longitudinal force is applied at the penstock. In load case B, both ends of the pipe are fixed. So, in this case, the longitudinal stress is 30% the circumferential stress. And in load case C, only a longitudinal force is applied. But with the developed analytical solution, and of course with the finite element solution, every general load case can be investigated. For the two construction details, an analytical solution is developed based on the classical shell theory. The radius over thickness ratio in penstocks is usually over 50. So the theory of thin shells is applicable. Here the static system of the thickness transition is shown. As you can see, the bevel isn't considered in the analytical solution directly, but I'll show you later on how the bevel can be considered in the analytical solution. And I developed solutions for the internal pressure and for the longitudinal force separately. So every combination of these two load cases can be determined. Here I just show you the equations for the moment and for the normal force in x direction and in the circumferential direction. With these equations, you can determine the stresses in the x direction and in the circumferential direction. I also developed an analytical solution for the ring stiffener. This is very similar to the analytical solution of the thickness transition. I don't show you this in detail, but you can find it in the paper. I also will concentrate later on the thickness transition. but the same things are done for the ring stiffener, and you find that in the paper. Here you can see the stresses determined with the analytical solution. The first two diagrams show the result for an internal pressure without any longitudinal force Nx. The stresses in the circumferential direction are shown in the left diagram. As you can see, the stresses in circumferential direction at the thickness transition are lower than the membrane stress in the thinner shell. This is a positive effect in case of an internal pressure. The stresses in longitudinal direction, sigma x, are quite small and are not relevant for fatigue design. And here I show you the stresses in circumferential and longitudinal direction in case of a longitudinal force Nx without Pi. Here the stresses in longitudinal direction are decisive. For this example, the nominal stress is equal to 75 Newton per square millimeter. And here an increase of the stress on the outside occurs at the thickness transition. This stress can be described with the load concentration factor K times the membrane stress. On this slide, I show you the comparison of the finite element analysis with the analytical solution. Here, on the right side, we've got the solution of the finite element analysis. Here it is shown for the thickness transition for load case B. The left figure shows you the longitudinal stresses. On the right side, the circumferential stresses are shown. And the stresses on the outside of the pipe are decisive for fatigue design. Here you can see the extrapolation for the structural stress. And these stresses on the outside of the pipe are compared with each other. Here in this diagram, you can see the longitudinal stresses on the outside of the analytical solution, and you see the stresses on the outside of the finite element analysis. Now this gray area is shown in detail in the diagram underneath. Here you can see the extrapolated stress in the hotspot of the finite element analysis. And also the analytical solution is shown with the black line. If you move the analytical solution to the middle of the bevel and you solve the analytical solution for this x is minus 37.5 millimeters, you can compare this stress of the analytical solution with the numerical result. And as you can see, the stresses are nearly identical. The same thing can be done for the stresses on the outside for the circumferential stresses. Also, this gray area is shown in detail here in this diagram underneath. And here also the extrapolated stresses of the numerical solution is shown and the stresses of the analytical solution. So the analytical solution delivers nearly the same result as the numerical calculation. So with the analytical solution, which delivers nearly the same results as the numerical calculation, stress concentration factors for different R/T ratios and for different bevel inclinations and for the three different load cases A, B and C can be determined. As you can see, the load cases with the internal pressure, load case A, without any longitudinal force, and load case B with a longitudinal force, delivers stress concentration factors lower than 1. That means that the membrane stress in the thinner pipe is bigger than the stress at the hotspot. Only in load case C, there is only a longitudinal force applied at the end of the pipe. The stress concentration factor is bigger than 1. And here you can see the influence of the thickness ratio T2 to T1. Now I show you a comparison of the nominal stress versus the structural stress concept for the detail of the thickness transition. Here this table shows the maximum membrane stresses for the nominal stress method and the structural stress method for different load cases A, B and C. To compare the nominal stress concept with the structural stress concept, the maximum membrane stresses for each method were determined, leading to a utilization factor of 1.0 in fatigue design. For load case A and B, the maximum membrane stress in circumferential direction is the reference. For load case C, the membrane stress in longitudinal direction is the reference. The structural stress method allows higher maximum membrane stresses compared with the nominal stress method. The reason for this in load case A and B is that the circumferential stresses in the hotspot are lower than the membrane stresses in the thinner shell. And in load case C, the thickness transition is considered in the structural stress method, and this leads to higher maximum membrane stresses. So there is a very good correlation between the finite element analysis and the analytical solution. The analytical solution can be used instead of the finite element analysis for the structural stress method for these two details. The structural stress method allows higher maximum membrane stresses compared to the nominal stress method. And this is also valid for the thickness transition. So I want to thank you for your attention.